This is the second video after canonical transformation, and we are going to talk about Poisson brackets and other canonical invariants. Then the infinitesimal canonical transformation and conservation theorems in the Poisson bracket formulation. Maybe exactly infinitesimal part we may not discuss today. Then angular momentum, Poisson bracket formulation. Now we have the Laplace transformation, which transforms Lagrangian into Hamiltonian function. You are all aware. That's HPQT, PQ dot minus L, Q dot T. So Lagrangian, which is a function of coordinate and velocity, is transformed to another function, Hamiltonian, which is function of coordinate and moment. And you have corresponding equations of motion. Like you have a Lagrange's equations of motion. Hamiltonian function will allow you to deduce equations of motion, which are called Hamilton equations of motion. And of course, dH by dt, since Hamiltonian is a function of q and t, the time derivative will depend on partial time derivative, derivative with respect to q, and derivative with respect to p. And now, if h is not explicit function of time, then dH by dt and dou h by dou t both are 0 and h is constant. Similarly, if you have a function f, which is function of q, p, and t, then you can write its time derivative in that fashion. But you already know from Hamilton's equations of motion that q dot can be replaced by dou h by dou p, and p dot can be replaced by minus dou h by dou q. See the minus sign here. That we would like to represent as, of course, the first term dou f by dou t, and the next two terms we are writing as minus h comma f in a bracket. It is this bracket which is known as Poisson bracket, and we will see its importance. But if you are familiar with commutator bracket in quantum mechanics, then commutator bracket has its origin in Poisson bracket. So the equations are very simple. You differentiate f with respect to q into dq dou q by dou t. Ultimately, it's a chain rule that you are using for differentiation. And then for q dot and p dot, you substitute partial derivatives from Hamilton's equations of motion. And that combination of this partial derivative term is what we represent as Poisson bracket. Right. So where your Poisson bracket now has a definition, if it is two quantities, h and f, then dou h by dou q, dou f by dou p. So first you differentiate with q, then p. In second time, first term we differentiated with p, and second differentiated with q, but with a negative sign. If f is not explicit function of time, then you remember df by dt was 0, dou f by dou t is 0, then of course commutator also will be 0. So if commutator is 0, if the Poisson bracket is 0, it means your function f is not good. I mean, of course, in this case, h is Hamiltonian. So a Poisson bracket between Hamiltonian and a function is 0. That means that function is not explicit function of time. For any, in general, for any two quantities, f and g, you would write Poisson bracket as this. Of course, we wrote p and q symbolically, but if there are n generalized coordinates and n generalized momenta, then you have to take n such terms and sum over. That is what is known as Poisson bracket. So when you have more than one coordinate and uh, generalized coordinates, say you have n generalized coordinates and n generalized momenta, Poisson bracket will have actually n such terms. Okay, not just one term. That should be kept in mind. Because normally we don't deal with problems with large number of dependents. But if there are more than one, then one has to be careful. So first function differentiated with respect to coordinates, second function with momentum, minus first function with momentum, second with coordinate. right? And in quantum mechanics, we have an equivalent equation, df by dt is dou f by dou t. F is, of course, an operator, uh, plus I h bar times fh. This is, of course, the commutator bracket in quantum mechanics. What we have is a Poisson bracket. Okay? And you know what commutator bracket is, but it has its origin in Poisson bracket, for your information. So properties of Poisson bracket, see, it involves basically derivatives. So when you have a sum of two functions, those derivative will split into two terms. So it is so obvious that f g plus s becomes f g and f s. Then, of course, if you flip the ones, the middle second term has a negative sign. So if you flip f and g, it will give you an explicit negative sign outside. And if one of them is a constant, then this is zero, obviously, because there are two terms and each term involves derivative of second function. In this case, second function is constant and therefore derivative has to be zero. And if it involves product function, then you know you have to go by UV rule. So you have u times derivative of v plus derivative of u times v. Okay, so the order has to be maintained. So FGS, and second time you have to take G outside on the left and then FS. So that is very important. You can actually just take P and Q, expand it and prove this. All right, it's better that you actually carry it out. And of course, if you take both F, then it has to be zero because there is a negative sign between the two terms. So they cancel out if both the functions are same. And of course, you can see here that the time derivative for any function would also, because there are product terms in both f and g. So first it is time derivative of f and then g. Then next time it is f times time derivative of. Same thing applies to partial time derivative also. And if you take Poisson bracket of x with Poisson bracket of y and z, and then of course you permute them cyclically, so you get two more Poisson brackets. Okay, then the sum is zero. Okay, this is actually obvious and expected. If you can't visualize this happening, then you actually open it out and see it yourself that it is indeed so. Otherwise, this is a obvious and trivial identity, but it's called Jacobi identity. Yes, that's a Jacobi identity. Equations of motion for Q and P. So obviously, if you do dq by dt, that's q dot. Hamilton's equation says it's dou h by dou p. That would be the commutator of q with h. And if you do that with p, okay, that will be commutator of p with h. There is an interesting one. Commutator of coordinate with a function is derivative of function with respect to momentum, corresponding momentum. And for momentum with that function, it is negative of derivative of f with respect to q. That's because you see, if you go by dou qk by dou q into dou f by dou p minus dou q by dou p, dou f by dou q, but dou q by dou p will become zero because if you differentiate coordinate with momentum, they are supposed to be independent, so that term will be zero. But since the q and p derivatives orders are interchanged, if you take p, you will get that extra negative. And if you take qk and pl, then that Poisson bracket is delta KL, which means if I take the say QK and PK, that means kth degree of freedom, coordinate and momentum, then Poisson bracket will be 1. But if I take any two coordinate and momenta which are not conjugate to each other, then their Poisson bracket will be zero. Okay? Any two coordinates, Poisson bracket is zero. Any two momenta, Poisson bracket is zero. All these three can be easily proved, established. You remember, whenever you take differentiation, you will have to sum over. Suppose you take differentiator with respect to Qj and Pj, then sum over all j values. So please, you may carry these calculations out and convince yourself it is so. But if you are capable of doing mental algebra, then this is obvious. Now let's take some problems. We are not going to solve them here in this video, but later on you can try them out. So given canonical transformation, so you are already given transformation from old coordinates to new coordinate and old momentum to new. This is old coordinate and momentum to new coordinate and momentum. Uh, then you find Poisson bracket of new coordinate and new momentum with respect to old coordinate and old momentum. So you take dou q by dou q, dou p by dou p minus dou q by dou p and dou p by dou q. Okay, so you have the functional forms, you take the differential and find the value. And you have found q and p. And if it is a functional form, then find its Poisson bracket with h, Hamiltonian. For the canonical transformation, this is another transformation. Again, you are asked to find, so you are not asked to find Poisson bracket, but you are given that the Poisson bracket has a value 1. In that case, you are expected to find value of this constant alpha and beta that appears in the functional form, right? Q raised to alpha. So the power alpha and beta, which is the coefficient of momentum. Uh, then you are expected to evaluate these commutators. Remember, in quantum mechanics, you have commutator amongst the angular momentum variables. In this case, you have Poisson brackets to be evaluated, right? So, but in this case, you have only three variables, x, y, and z. So you have to be careful about carrying out differentiation and do it. But for example, when you take x and ly, you will have to take two terms. For once you have to take x and px Poisson bracket, and the second time you have to take y and py derivatives for the commutator. Remember, angular momentum is r cross p. So if you take ly, it would be zpx minus xpz, and then you will have to split it out using the properties that we have seen earlier. When you have a product term of two or the summation of the two terms. So it's a bit of laborious calculation, but students should carry it out once to become familiar with this kind of. Then, of course, you have another transformation given, and you have to show that it's a canonical. All right. So for transformation to be canonical, it has to obey that Poisson bracket which we have written earlier. Which one? I'll tell you. This QP QKPL is delta KL. QKQL is 0 and PKPL is 0. So if that is obeyed, so in this case, you have the same, there is only one coordinate and momentum. So the Poisson bracket of Q and P should be 1. All right. If the transformation is canonical. So you have to take Q and P, find its Poisson bracket with respect to small q and small p, and check if it is 1. If it is 1, then the transformation is canonical. Right. So you are given a function f equal to x minus p by mt, one-dimensional problem. So only one coordinate and one momentum. And you have to show that the partial derivative is minus fh. And your charge particle in constant magnetic field. Constant magnetic field is has a vector potential which is always half b cross r. Then you have to find a Poisson bracket of Vx and Vy. So Vx and Vy would be like taking x dot and y dot, right? And R is xi plus yj plus zk. B is constant magnetic field, so you can take B in Z direction. So B vector as B times K. Then you find out what is A. All right. I think there could be a typographic here. I'll verify the problem because as of now with this problem, yeah, okay. So you will have to actually evaluate the velocity as a function of time in magnetic field. Normally, if you have a field in Z direction, then particle will perform circular motion in XY plane. So then you will have corresponding Vx and Vy values, and you find its Poisson bracket. All right. This is going to be a much shorter video, except that a lot of things are mathematical, and here I can't keep on doing those calculations. So I expect students who go through this video will sit simultaneously with pen and paper and keep calculating and verifying what is being shown. So you have FQPT and GQPT, two functions, which are both functions of old coordinates and old momenta. Uh, and F and G both are constants of motion. Then you have to show FG Poisson bracket is also constant of motion. F is a constant of motion, G is a constant of motion, F and G is also a constant of. So here is the proof. df by dt is given by this, and so would be dg by dt, almost the similar relation. So you take d by dt of f and g, that will, I mean, Poisson bracket also would have a functional form. In that case, Poisson bracket fg is also a function. So it has to be treated like a function. So total derivative is partial derivative times Poisson bracket with h. H is Hamiltonian, of course. And then you can actually do the differentiation as we have seen in one of the properties. So partial derivative will split it into two brackets, and then you have, of course, the last term as it is. And then for the last term, we use Jacobi identity. So what would Jacobi identity do? It will give you FGH as FGH and GHF. But G and F are constant. So what will happen to GH and HF? Remember, Poisson bracket with a constant function is 0. So the two right-hand sides will become 0. So FGH will also be 0 if the functions are constants, right? So that's what you will get. First term, second term, and then the this commutator being replaced by corresponding terms using Jacobi identity. Remember, this is F, comma G and H, whereas here the single term comes on the right because there was a negative sign. No, if you take two terms on the right hand side, there will be an extra negative sign. So that would allow you to flip the terms. Right? Let's see what it's going to lead to. All right. So it's gone one step further. And since there is a commutator with F here, okay, both the terms are combined together. And both the terms with G are also combined together. And of course, here you have taken G on the left, and therefore there will be a residual negative sign. So first term with a negative sign, but the second term HF Poisson bracket will come as it is, right? And minus dou f by dou t plus HF is nothing but minus df by dt. So basically, what you will end up getting is minus, since this is minus df by dt, that negative sign is coming out here. This is plus dg by dt. Sorry, this term should have been total derivative, dg by dt. Right? And since f and g both are constants of motion, df by dt and dg by dt both are 0. And therefore, this time derivative of f and g, which are constants of motion, their Poisson bracket, time derivative of Poisson bracket will also be 0. Okay, this appear to be an obvious one, but we have shown this as a proof. So if f and g are two constants of motion, then the Poisson bracket of f and g will also be a constant. Next, we are proving an important identity, which is invariance of Poisson bracket under canonical transformation. And in fact, this will become one way to verify whether a transformation is canonical or not. You know, Poisson bracket of Q and P is 1. Uh, so if you transform them into new coordinate and new momenta, their corresponding Poisson bracket also should be 1. 0 if they are different, mismatching coordinates and momenta. They are not conjugate to each other, then Poisson bracket should be 0. So that would become, in a way, your prescription to verify whether transformation is canonical. So the rule is transformation is canonical and the Poisson bracket with respect to Q and P will be same as Poisson bracket with respect to capital Q and capital P. Okay, now here we are going like a purist. So if you transform your old coordinates and old momenta to new coordinates and new momenta, actually the functional form would change. So whatever is the functional form of f and g, they would change. We would represent them by f bar and g bar. Okay, so for mathematician, it's very important. For physicist, we say, okay, look, I'm talking about the same function. Uh, and you want to prove that both the Poisson brackets will be same. So let's see, dou f by dou q is given by dou f by dou capital Q, dou q by dou small q. Okay, you are taking partial derivative with respect to q. So with respect to capital Q and capital Q with respect to Q, so that's a chain rule. And similarly with momentum. Okay, and there are Maxwellian relations. Uh, so dou Qj by dou Qi will be dou small pi by dou capital Pj. And uh, if you mismatch, I mean here Q with Q and P with P, so positive sign. If you have P with Q and P with Q, then there is a negative sign. So your dou f by dou q, if you substitute this second factor in the summation for each term by using this Maxwell's relation, your dou f by dou q will become dou f by dou q, dou p by dou capital P, and so on, which means essentially this is your Poisson bracket of f with respect to small p, okay, taken in a new coordinate system, capital Q and capital P. Of course, this is a small old coordinate, old momentum. Capital Q and capital P are your new momenta. Uh, this is one quantity. Similarly, you do dou f by dou p, and by the same rule, Maxwell's relations, you will get that as Poisson bracket of Q with f with respect to new coordinates. All right. So if you do f and g Poisson bracket, then you can transform the terms using Maxwell's relations. All right. Of course, dou g by dou p and dou g by dou q are yet to be translated, but dou f by dou q and dou f by dou p, we have already found these two terms. I'll just check. Yes. With respect to q, there is a negative sign. And if you see, with respect to p, there is a positive sign here. Should it be a positive sign? Yeah, that's positive, but then the first term here brings a negative sign. So there is probably a mismatch of sign here. Let me check. Dou f by dou q. Yeah. So the second term here should have been a negative sign here. This second term in the last equation second small bracket, second term should have a negative sign. Doji by dopey and doji by doq has to be translated exactly like what you have done with F. And if you do so, then simplification will show you that, of course, you still have to substitute. So there will be bracket for doji by dopey and doji by doq, which will carry two terms each. And then you open it out, and you will find that the only surviving term will be the two, which is with respect to new coordinate and momentum. Okay, so that gives you your Poisson bracket with new coordinate and new momentum. So Poisson bracket with old coordinate and old momentum is same as Poisson bracket with new coordinate and new momentum, which means the Poisson bracket is coordinate independent. Now, if you say, look, G is equal to H, which is the Hamiltonian of the system, then F and G Poisson bracket will be dF by dt. Of course, that we have seen earlier, uh, which does not depend on properties of choice of coordinate system. So even time derivative of a function does not depend on properties of choice of coordinate system and depends only on the properties of motion of the fictitious system. So in a way, you can say that irrespective of your reference frame, it will have the same value. All right. So this is invariant quantity. All right. So as far as Poisson bracket is concerned, that much only. There are already problems given to you. Please try it as a homework, and difficulties can be discussed. Thank you.